Hello everyone, and welcome back to another video. Apologies for a bit of a break, though it wasn't much of a break. I was kind of sick, and that's why there hasn't been uploads. But I'm back now, mostly. If I sound sick, you know why. Anyway, we have this cool integral today that we're going to be evaluating two ways. One with real techniques, the other with complex techniques. So, let's get started. Let's just get started. So the first way we're going to do this is with, as I said, real techniques, and we're going to be using the beta function. So yes, let's get started with changing the bounds though. So we can change this, because this is symmetrical with this x squared and this being over all real numbers, we can change this to 2 times the integral from 0 to infinity of 1 over 1 plus x squared to the n plus 1 dx. And then what we're going to do next is, just because our beta function is typically in the form without any extra exponent, so it's just like normal x's inside that. Like we don't have x squared raised to another power, it's just 1 plus x all raised to a power. We're going to do a quick u sum, so we're going to let u equal x squared. Then du is equal to dx, and then we have this extra factor of 2x right here, meaning our integral is just the integral from 0 to infinity still. The 2's cancel. Of x to the, apologies, it's really u to the negative 1/2, and there's a reason I'm writing it like that, over 1 plus u to the n plus 1 du. And the reason I'm writing it like that is simply because we can express the beta function like this. We can say beta of some x comma y is equal to the integral from 0 to infinity. Oh my goodness, that's not a good infinity sign. That's better. Of some t raised to the x minus 1 power over 1 plus t raised to the y plus x power dt. We can define the beta function like this. I'm not going to prove it in this video. You can just take Wikipedia's word for it. And what we can do is really just pattern match. Say, or basically let x equal, well, I say x. We can let x equal, say, or this whole term right here equal negative 1/2. Meaning that our x in total is just going to be 1/2, because 1/2 minus 1 is just going to be negative 1/2. And we can do the same thing sort of at the bottom. So we can say x plus y is equal to n plus 1, but we already know that's a half. So subtracting that from both sides, we find that y is actually just n plus 1/2. So evaluating this, and scrolling down a bit, we now have that our integral is just equal to beta of 1/2 comma n plus 1/2. And by properties of the beta function, we can express this in terms of the gamma function, meaning that we have gamma of 1/2 times gamma of n plus 1/2 over gamma of n plus 1, since the 1/2s just combine together to make 1. And we could, just kind of stop here, but that is kind of, a little bit boring, and also whenever we do this using complex techniques, we're going to get a result in a different form, so it's best to simplify this either way. And the way we're actually going to do that is take a look at this term right here, this gamma of n plus 1/2. And the reason for that is because this actually has a nice expansion formula, namely, moving on over here, namely gamma, select a pen, gamma of n plus 1/2. This is also, you can also find this on the Gamma Wikipedia page, very helpful, would recommend. Gamma of n plus 1/2 is equal to 2n factorial over 2 to the 2n, n factorial, and then times the square root of pi. Why this is so, I suppose we'll prove later on, I suppose. Or we'll probably prove like the general version, and then we'll Might circle back to that. Oh, that'd be a good video, actually. Anyway, before I get sidetracked anymore, we can simplify this quite a bit now. So substituting in that gamma of 1/2 is just the square root of pi as well. And combining with that square root of pi, we have that this whole thing is just equal to pi times 2n factorial over 2 to the 2n times n factorial. And instead of writing this gamma of n plus 1 as gamma of n plus 1, we know that we can just write that as n factorial. So we can just combine like terms and make that squared right there. And that here is actually just our answer. Pi times 2n factorial over 2 to the 2n times n factorial squared. So now let's go and do it with some complex techniques. And now we're back. Let's do this with some complex techniques. What we're going to do is just note that this right here actually just has a simple pole, namely at x equals I. Really, it's plus or minus I, but what we're going to do is really just the usual semicircular, that's not a semicircle, the usual semicircular contour integration, where, again, our pole is just a simple pole at x equals I. So, in order to do that, we're going to be assuming that this right here is 0, the semicircle bit. But what we're going to do then is just apply the residue theorem to this at x equals I, and then multiply that by 2 pi I, and we'll get our answer. So actually writing this out a bit more formally, we have our line integral. It's just equal to I, which is just, our integral right here. But again, the semicircle goes to 0, so we're just left with I is equal to 2 pi I, and then times the residue at I. So we just have to find the residue at I, and then it's all good. So I'm actually going to write out sort of like the entire residue theorem for once, because we do need like every single bit. So we have 1 over n plus 1 minus 1 factorial. I'm writing that just so as to not get confused. And then we have the nth derivative, because n plus 1 minus 1, that's really the degree of our pole, dx to the n. And we have x minus I to the n plus 1 over x squared plus 1 to the n plus 1, close parentheses. But we can just write x squared plus 1 as, well, we can factor that. We can say that's x plus I, x minus I, and distributing the n plus 1 in the exponent, we find that it actually cancels with, or the x minus I, when we factor it, cancels with the numerator, really just leaving us with, I'm just going to erase it, just leaving us with 1 over x plus I all to the n plus 1, and just this actually is a limit as x approaches I. So all we have to do then, I'm actually going to clean this bottom bit up as well, just for clarity's sake. What we're going to do is just evaluate this nth derivative, which I feel like we often do on this channel, but it's always kind of fun. And the way we're going to do it is really just rely on the definition of, say, the derivative of some polynomial. And what that is really is this. I'm going to write it to the side. Say we have like d over du of, say, u to, or the nth derivative, I should say, of u to some a power. That right there, we know by power rule, if we just keep applying it, what we're going to get is we're going to get an a originally, and then a minus 1, and then a minus 2, and so on and so forth, up until a minus n. And what we call that is just a falling factorial. So expressing this as an, we can apply this for non-integer values of n, and get a correct result. And what we have as well is just a u, and then to the a minus n. That part should be more or less intuitive, because if you differentiate, I don't know, say x to the 7th, you're going to get an x to the 6th term with 7 out front. So that's what it is in general. So applying this directly here, what we have is a d over dx and then ends there. And then we have an x plus I to the negative n plus 1. And I'm writing it like that for a very specific reason, because, I mean, it is rather important. So what we're going to do then is just say, okay, kind of pattern match this formula right here. Well, our a right here is just going to be this n plus 1. So we have our negative n plus 1. I don't know the actual name of this operator. If someone could like leave that down in the comments, like, I guess negative n plus 1 sub n, I suppose, something like that. But if there's an actual like proper terminology, please let me know down in the comments. And then we just have our x plus I term, but then to the negative n plus 1 minus n. So that's actually just going to be x plus 1, but we're taking the limit as x approaches I, so we can actually just plug it in here. So I plus I is 2I, all to the negative n minus 1. And then we also have this 1 over n factorial out front, just from here, bringing that down. So it looks like we are almost-ish done, because, you know, we have, we've essentially eliminated the derivative, but there are a few tricky things left, and I'm going to kind of clean those up now. First off, what I'm going to do is kind of evaluate this I'm going to evaluate this 2i to the negative 2n minus 1 term. And to do that, what I'm going to do is expand it out. So this right here is equal to 1 over 2i from the negative 1, but then 2 to the minus 2n times I to the negative 2n. But what is I to the negative 2n, where what we're going to assume is n is some sort of integer? Well, we can apply this negative 1 here and say we have 1 over I to the 2n, but 1 over I is just negative I, and whenever we square that, it doesn't matter if there's a positive or negative I there, the negative is going to get canceled out anyway. So what we're really left with, no matter if there's a negative or positive in front of the 2n, is negative 1 to the n. So this right here is actually just 1 over 2i times 2 to the 2n, but then times negative 1 to the n. So, putting this all together, we have our integral is equal to 2 pi I times 1 over n factorial times negative n minus, or negative n plus 1 sub n, and then times 1 over 2i, 2 to the 2n, negative 1 to the n. And the reason I wrote this 2i down here like I did is so that we can just cancel it with that right there. And you'll see our solution actually starting to take the form it did previously when we did this with real techniques. The really difference being that we have this wacky negative 1 term and that right there, the following factorial. So let's actually get evaluating the following factorial. So the definition of a following factorial is essentially this first term, so n plus 1, or negative n plus 1, pardon me, factorial, then divided by the first term, so this negative n plus 1 here, minus the bottom term. So in this case, it would be negative 2n minus 1. And what you'll notice here is that we do have a bit of an issue, because if we say, well, let n be just some integer, right? Some integer, or some positive integer, I should say, some natural number, right? If we let it be, I don't know, say like 3, right? Let n equal 3, we have negative 4 factorial in the numerator, and we have, what would they be? They'd be like negative 9 in the denominator. And you'll note that that actually is just 0 over 0, because the factorial of any negative integer is just going to be, well, undefined. Its reciprocal is defined as 0, but that's not very helpful to us because we have 0 over 0. So what we're going to do actually is exploit this negative 1 term and the fact that we have a falling factorial here, and use the following property, and that is namely that x sub y is actually equal to negative 1 to the y, and then times negative x, not to the y, but this right here denotes a rising factorial. So what we're going to do now is really just combine those terms, because you'll notice that we can actually just multiply both sides by negative 1 here, so cross that out, say negative 1 to the y. And note that this right here is the exact same. So instead of expressing this as some 0 over 0 term that we can't really evaluate, what we can do is use this. So this means that this term right here is equal to negative x, or negative n plus 1, not to the, but I guess superscript n. And then we have our pi over our 2 to the 2n n factorial out front. So this just leaves the question of what on earth is that? And the answer is just going to be, right here is defined to be the sum of these two things. So that would be I do apologize. This should be a positive right here, as there's a negative right there, and also a negative right there. I do apologize. So what we have here then is this, which is defined to be, let's try this again, the sum of the two things, so 2n plus 1, and then minus 1 factorial, divided by this term right here, minus 1 factorial, so n factorial. And you'll note that this actually is just our solution that we got previously. So this now is equal to pi over 2 to the 2n, n factorial squared, and then 2n factorial. And there we go. We have done this integral in two different ways using completely different techniques. We got the same thing. So anyway, I hope all of y'all enjoyed this video, and I'll see y'all in the next one.